Swayam Prabha. Digital India. Educated India.
Using an energy profile, write out the various products of nitration of trifluoromethylbenzene. So, trifluoromethylbenzene has a trifluoromethyl group. So, we see here that fluorine is highly electronegative. So, it's going to pull electrons through induction. And so, any group that is attached to a CF3 group is going to be electron deficient. So the example that we can look at is that if I compare a regular secondary carbocation such as this, and instead of instead of hydrogen I put in a CH3 group, the CH3 group is electron donating, and this stabilizes the carbocation substantially in the form of donating electrons and delocalizing the positive charge, whereas the trifluoromethyl group withdraws electrons and destabilizes the carbocation. So therefore, the trifluoromethyl group is considered as a fairly strong electron withdrawing group. Now, when it comes to nitration of trifluoromethylbenzene, so what we're talking about is, if I take this compound and expose this to the standard nitration conditions, what are the possible products? Now, let's consider the first situation, which is the ortho-substituted compound. So here, once the attack happens, there is going to be a positive charge that develops right next to this attacking carbon, and you can delocalize this carbocation by pushing electrons in the following manner. So there is one structure that you will clearly see here where the CF3 group is directly attached to the carbon bearing the positive charge. So therefore, the ortho attack will lead to a situation where the intermediate is somewhat unstable. If you consider the para attack, similarly, when the nitro groups reacts with this carbon, there's going to be a positive charge that's immediately developing here, which can then delocalize and go into this resonance form, wherein the CF3 is directly attached to the positive charge. So this again leads to a less unstable or less stable situation. So both ortho and para attack is going to give you a very unstable intermediate. Now, when you consider the meta attack, you will find that the ortho position, to this right next to it is a positive charge. Once you delocalize it, you're going to get a positive charge over here. And now when the next delocalization can happen, and where there is a positive charge here. So in none of these resonance forms, the CF3 is directly next to the positive charge. Therefore, this structure is less unstable compared to the other two structures. Now, if I try and understand the rates at which these are going to react, when compared to benzene, assuming that the relative rate is 1, the ortho position reacts at a rate of 4.5 times 10 power minus 6. So that's about a million-fold slower. The meta position is going to react about 10-fold faster than the ortho position, and the para position is going to react at the same rate as the ortho position. So therefore, it's not like the meta position is highly stable, it's just that the substitution at meta is a little bit faster than that of ortho and para, and therefore the meta product dominates. Now coming to the energy profile, so if we consider a regular benzene ring to form the nitration of benzene ring, so we already know that this is the activation energy and this is going to be the complex that is formed. Now when we consider the CF3 group and electrophile is nitro, when it attacks at the ortho position, there's going to be a positive charge right next to the CF3, and this is going to contribute to the lack of stability of this, and therefore with respect to benzene, one can imagine that this energy is going to be higher. Similarly, in the para, we already discussed that one of the resonance forms has a positive charge next to the CF3, and therefore this also is going to be quite unstable. Lastly, when we consider the meta intermediate is somewhat more stable when compared to the ortho and para, and therefore the barrier to cross the meta is lower than that of ortho and para. The nitration of benzaldehyde produces the meta product as the major product. Write out the intermediates for this reaction and compare their stability. So here in this question, benzaldehyde is reacted with HNO3 and H2SO4, and the meta-nitro product is the major product. So we already know that the aldehyde is going to be electron withdrawing, so when we look at the three intermediates that are possible for ortho, meta, and para, just like the trifluoromethyl example or the other previous examples that we have taken, we need to consider the resonance form where if there is a positive charge right next to the electron donating or electron withdrawing group, that is going to be more important. So clearly this positive charge here right next to the aldehyde is going to be unstable, and therefore the ortho attack is not favored. Similarly, when you look at the para nitro substituent, the positive charge is again right next to the aldehyde, and therefore this intermediate also is less stable. However, in the meta attack, the positive charge does not have an opportunity to interact directly with the carbonyl carbon, and therefore it becomes the more stable intermediate. Provide a rationale for the selectivity of the following reactions. The first example here is the bromination of 4-nitro-toluene, and it gives this product exclusively in about 86 to 90% yield. In order to address this problem, the strategy that we would adopt is to find out what kind of groups are ortho-para directing and what are meta-directing. So to begin with, let's look at the methyl group. The methyl group is clearly ortho-para directing, and therefore the two red arrows as shown here are going to be the preferred positions for attack. The nitro group, on the other hand, is going to be meta-directing, and also it is going to be directing the bromination at the positions as shown by the arrow. Now, given that the methyl group is an electron donating group and its effect on the aromatic ring is greater, it's likely that this is going to dominate. But what is important here is that the nitro group does not hinder the attack of bromination because the nitro group is also meta-directing. So therefore, in this particular case, the two groups reinforce each other, and the bromination exclusively happens at this position, which is ortho to the methyl group. In the next example, we are going to look at metaxylene and where the nitration occurs on metaxylene. So in the case of metaxylene, it produces this product here, that is 2,4-dimethyl 1-nitrobenzene in 98% yield. So again, the approach here that we need to take is to write out the structure and find out what each of those groups, each of those positions here, what is going to be the nature of the directing ability. So both methyl groups here are ortho-para directing. So if for the first position as shown here, this substitution here would occur if both the methyl groups are ortho-directing. Okay. Similarly, if one of them is ortho-directing and the other one is para-directing, this is going to be preferred. And this here will happen, a substitution will happen here if both the groups are meta-directing. That is, if a substitution happens here, it is meta to both the methyl groups. And lastly, this substitution here is going to be ortho to one of the methyl groups and para to the other methyl group. Notice that this hydrogen here is essentially identical to this hydrogen because they both are ortho as well as para to the methyl group. So basically we have three choices here, and one can conclude that the meta directing or the meta substitution is unlikely given that methyl group is orthopara directing. And now between these two choices, we would prefer this one here. And the reason for that is that there is some steric hindrance that happens when you have a substituent at the ortho position. That is, you have two substituents at the ortho position, and therefore the attack on this carbon is unlikely. So this model helps us explain the excellent yield of 2,4-dimethyl 1-nitrobenzene in this reaction. The next problem, we're looking at proposing a synthetic route to metanitroacetophenone from benzene in 2 steps. So metanitroacetophenone is this structure. So 1, 2, 3, 4, 5, 6. So it is the nitro group is in the meta position. And how do you make this from nitrobenzene? So we could consider 2 different routes. The first route is that we can take, or we could suggest, is the nitration of benzene, which will give us nitrobenzene, and this reaction works really well. The next step is a Friedel-Crafts acylation reaction, which can be tried with acetic anhydride and aluminum chloride. However, we observe no reaction, or we expect that there will be no reaction because the nitro group is highly deactivating. On the other hand, if we take the other route, that is, we first do the Friedel-Crafts acylation and produce acetophenone from benzene, this yield is also pretty okay, which is about 75 to 80%. And then we follow it by nitration. The acetophenone, the acetyl group, although is electron withdrawing, we've already looked at it, and it's not as strong an electron withdrawing group as the nitro group. And therefore, this reaction can occur, and although the yield is not that great, it's still something that can move forward and give you the desired product. So between the two choices, this reaction occurs preferentially. This second scheme is preferred. Predict the product of the following reaction. So here we are dealing with a competition between methoxy group and methyl group, and the reaction with this olefin in the presence of H2SO4. So as you would have correctly guessed or predicted, the olefin is going to get protonated and it's going to produce a tertiary or a carbocation as shown here. Now you have two choices. This methoxy group, the electrons from the O oxygen can enter the benzene ring through conjugation, and it can react with tertiary butyl with this carbocation to give you an intermediate such as this. So this is the new bond that is being formed, and there's going to be a full positive charge on the oxygen. This is one choice. And the other choice is the reaction of this double bond with the same tertiary butyl carbocation, which results in the formation of this intermediate. Now, if I have to compare the stability between this intermediate and this intermediate, clearly this one is more stable than, the involvement of the electronegative or the lone pair from oxygen is very important. And also, the stabilization by this group is far more than the methyl group. So it is not surprising, therefore, that this is the exclusive product that is formed under these circumstances. What combination of acid chloride and arene would you use to prepare the following compound? So here is another example of two choices that we could have. So if I have to do a Friedel-Crafts acylation reaction, then I'm going to be breaking, or I'm going to be forming this bond over here. Okay. Now, if this is the bond that's going to be formed, then I would have to start with benzene and react it with 4-nitro benzoyl chloride. Okay. Now, this is one choice. The second choice is that if we can break the bond as shown here. Now, this is going to be produced if you start with 4-nitrobenzene and react it with benzoyl chloride. Okay. Now, let's just write out these choices in the next page. Now, when we react 4-nitrobenzene with benzoyl chloride, nitro is a very strong electron withdrawing group, and therefore Friedel-Crafts acylation reactions do not occur under these conditions. So therefore, there is no reaction that happens. Whereas in the other scenario, where we start with 4-nitrobenzyl chloride, benzoyl chloride, and react it with benzene, the reacting group is actually benzene over here, and therefore this reaction occurs without difficulty, and the yield of 4-nitrobenzophenone is 87%. So the problem here is to identify the product of this reaction and propose a reasonable mechanism for the transformation. Okay? So the way we would approach this problem is to look at the major functional groups in this reaction. So the major functional group in this reaction is actually the carboxylic acid. So if we were to draw the structure of the carboxylic acid and imagine what might happen to it when you heat it, so one possibility is that it clearly get protonated. So you can imagine that this can pick up a proton and it will give you the corresponding protonated OH2 plus, right? And the rest of the molecule might remain the same. And this protonation reaction would likely be a reversible reaction. So it's going to go back and forth, back and forth. But since we have heated the molecule, we're heating up the reaction, it's possible that you can imagine that this lone pair comes in here and kicks out water. Okay, so the resulting structure that would emerge would be the benzene ring remains intact, and you get a C triple bond O plus, right? And then the phenyl ring remains here, and the byproduct is water. Okay, so now depending on how reactive this molecule is, it can sometimes react again with water to give you back the starting material. But since we are familiar with the Friedel-Crafts acylation reaction, you will immediately recognize that this is the acylium ion, which is a key sort of player in the Friedel-Crafts acylation reaction. So I'm just going to redraw the structure in a different format so that it's easier for us to understand the reaction. So the benzene ring remains the way it is, right? And your C triple bond O is here, and now CH2, CH2. I'm just going to draw out this benzene ring so that it becomes easy for us to follow it. Okay, so now let me quickly number these carbons. So I will start with the C triple bond O. So there's number 1. Carbon next to it is 2, 3, 4, 5, 6, 7. Okay, so now if these are 7 carbons, and now of course you can go on numbering this further, this becomes 8, 9, and then 10 and 11 are the same as 8 and 7. Okay, so this is perhaps the one good way to number it. Of course there could be others, but this provides us the context. So if Friedel-Crafts acylation would to occur, so just to remind you, the Friedel-Crafts acylation occurs in the following manner. So you have, let's say, C triple bond O, R plus, that is the electrophile, and your compound attacks here, and it gives you a very important intermediate, which is H C double bond O R, and there's a positive charge that ends up over here. Okay, so if you were to imagine that a similar situation would occur here, then the bond between carbon 6 and 7 would break and it would attack on this carbon, and this bonded pair would go and end up on oxygen and neutralize it. Okay, so the resulting molecule that would form is basically the benzene ring on the left remains intact. Okay, and now you will form 1, 2, 3, 4, 5, 6, 7 member ring. So let me just draw out the 7 member ring. There's a new 7-member ring that is formed, and the benzene ring remains the same way. And now we need to number this. Okay, so the bond between carbon number 1, that is over here, has the double bond, and number 2 remains the same. 3, 4, all unchanged. 5, and when we get to 6, 6 is over here. And now the important carbon is carbon number 7. Okay, so if you see here, this becomes a sp3 carbon. So carbon number 7 would be sp3. Okay, now the remaining molecule is going to be the same. So I'm just going to draw out the double bond over here. Okay, so now it forms a 7-member ring, and there's a positive charge that still remains, and that's going to reside on carbon 6. Of course, you can delocalize into this aromatic ring. But now, if we were to push arrows to regenerate aromaticity, then you would go over here and give you the final product, which is going to be the following. Okay, so I'm just going to make some space over here so that we can use the entire sheet. Now, the final product is going to be based on this mechanism. It's going to be this. Okay, so now let's count the number of carbons. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So C15, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12, and oxygen. So you can go back and do your molecular weight using this formula, and you will end up with a molecular weight of 208. Okay, and therefore your M by Z that's going to show as per the data that's given is 208.09. So that is the answer to the first question. Right, let's move on. So here, in this case, the question is, how do we synthesize this compound? Okay, so in order to address this question, we need to, of course, start from benzene. So let's try out the first strategy, which would be to start from benzene and then basically chlorinate it, right? And you get chlorobenzene. The reagents would be chlorine and AlCl3, for example. And then we do a Friedel-Crafts alkylation, right? And that is going to give you the product that you want, but it's the regiochemistry is going to be wrong. So since chlorine is actually ortho-para directing, you'll end up with a mixture of para plus ortho. Okay, so this strategy clearly is not going to work. Now let's consider the reverse situation. That is, first we do the Friedel-Crafts alkylation. So FC alkylation, that's going to give you ethyl benzene, right? And then we dex do the chlorination, and this is actually again an ortho-para directing group, and so you're going to end up with the same mixture as shown here, okay, plus the ortho compound. All right, so clearly neither of these strategies is going to work, so we need to figure out how to do this reaction in a way that is going to give us the right regioisomer. So in order to do this, let me consider the other possibility, which is to work out, let's say we start from acetophenone and then do the chlorination, and you will end up with the correct regiochemistry, which is the meta product, because this is basically an electron withdrawing group, and the electron withdrawing groups are meta directing, and so you're going to end up with the meta product. And how we would then, you can then just do a reduction to give you the final desired product, which is this. Now, the way we would get to this compound is fairly straightforward. We start with benzene and do a Friedel-Crafts acylation. Okay, we start with CH3, C double bond O Cl in the presence of AlCl3. That's going to give you this compound. So, in one important way in which we could make this compound is through Friedel-Crafts acylation as the first step, and that's going to give you acetophenone, followed by chlorination, which is going to give you the meta-chloro compound. And the last step would be reduction. Here you have a choice of either doing Wolff-Kishner reduction or Clemmensen reduction. So this strategy will work.